The nutritional value of fruit peels is far from uniform. It is shaped by a complex interplay of species, cultivar, seasonal timing, and environmental factors such as light, temperature, and soil minerals. The hypothesis that peel nutrient profiles differ significantly between tropical and temperate fruits, and even among cultivars of the same species, is increasingly supported by biochemical analyses. These differences are not trivial. They influence the antioxidant, vitamin, and fiber content of peels, with direct implications for their utility in functional foods, nutraceuticals, and sustainable food systems. By understanding these seasonal and varietal differences, we gain not only insight into plant physiology but also strategic guidance for peel valorization and crop selection. One of the clearest examples of varietal influence is seen in apples. Red apple cultivars, such as Red Delicious or Fuji, develop anthocyanins in their peels, pigments with strong antioxidant properties, while green apples like Granny Smith typically do not. This difference arises from both genetic regulation and environmental cues, particularly sunlight exposure, which upregulates anthocyanin synthesis in red cultivars. Beyond color, polyphenol content also varies. Red apple peels have been found to contain significantly higher total phenolics and flavonoids than green ones. Meanwhile, early harvested apples tend to have firmer peels with higher fiber and polyphenol content, while late-season fruits may accumulate more sugars and have thinner skins, reflecting a trade-off between maturation and nutritional density. In the case of citrus, peel nutrient content is shaped both by cultivar and geography. Oranges, mandarins, and lemons grown in tropical climates tend to accumulate more essential oils and carotenoids in the peel due to greater sun exposure and thermal stress. These factors stimulate the production of protective compounds like limonene and S-cryptoxanthin. For example, oranges cultivated in Brazil or southern India often have deeper orange peels, which corresponds to higher provitamin A carotenoid content compared to subtropical varieties from Spain or California. Comparative studies have also shown that vitamin C and phenolic levels in citrus peels can vary by as much as 30 to 50% depending on region, harvest timing, and cultivar, suggesting both environmental and genetic controls over phytochemical synthesis. Tropical fruits such as mango, papaya, and guava offer a particularly rich case for peel nutrient variability. Mango peel carotenoid content is not only much higher than that of the pulp but varies dramatically by cultivar. Alfonso and Tommy Atkins varieties, for example, show greater concentrations of SS-carotene and lutein than lower pigment varieties. Climatic conditions also influence nutrient synthesis. Higher altitudes and greater diurnal temperature fluctuations often increase peel antioxidant activity, possibly due to plant stress responses. Guava peels likewise exhibit variation based on whether the variety is pink or white-fleshed, with the former generally showing higher lycopene and vitamin C levels. Papaya peels are rich in proteolytic enzymes, e.g., papain, but enzyme activity varies significantly depending on ripeness at harvest, cultivar, and exposure to heat during growth and drying. Grapes present one of the most studied models for varietal peel phenolics. Red wine grapes like Cabernet Sauvignon are prized for their thick peels packed with resveratrol, anthocyanins, and tannins. Yet even among red cultivars, peel phenolic composition varies markedly due to both genetic factors and terroir, soil, sunlight, rainfall, and altitude. Research comparing European and South American vineyards reveals that identical cultivars yield skins with different antioxidant capacities and polyphenol profiles, illustrating how climate and environment shape bioactive compound accumulation. Seasonality also plays a role. Drought conditions or high UV exposure in a given year can elevate peel polyphenol concentration as a stress adaptation. The role of ripening stage and harvest time cannot be overstated. Early season harvests typically result in peels with higher fiber, polyphenol, and organic acids, whereas late season peels may have more sugar and water content. This is particularly relevant for processing applications where peel powders are used as functional ingredients. Timing the harvest for optimal phytochemical density can improve efficacy and economic value. Processing methods like freeze drying, when applied to peels harvested at peak maturity, help preserve these nutrients, while oven drying can lead to partial degradation depending on temperature and duration. A key research frontier lies in comparing identical species grown across different latitudes or climatic zones. For instance, pomegranate peels harvested in arid Middle Eastern climates tend to contain higher punicalagin levels, an antioxidant polyphenol, than those grown in humid subtropical zones, possibly due to stress-induced secondary metabolite synthesis. Such comparative studies would clarify the relative influence of genotype versus environment, G times E interaction on peel nutrition, and could guide crop breeding programs aimed at maximizing peel value. Similarly, experiments comparing vitamin and polyphenol content of citrus or guava peels across tropical, subtropical, and temperate zones would provide insights into climate-resilient phytochemistry. The practical implications of this hypothesis are far-reaching. Identifying cultivars with nutrient-dense peels allows breeders and growers to select for varieties that serve both dietary and sustainability goals. This would enhance the economic value of fruit byproducts and reduce waste through upcycling. In functional food development, sourcing peel powders from specific cultivars or regions could ensure higher bioactive yields, whether for antioxidant supplements, dietary fiber fortifiers, or therapeutic extracts. In conclusion, fruit peel nutrition is not static. It is a dynamic expression of genetics, seasonality, and environmental context. Varietal and geographic differences in polyphenol, vitamins, fiber, and minerals profoundly influence the nutritional potential of peels, particularly in the context of functional food and supplement development. Embracing this diversity through targeted analysis and crop selection opens the door to a more informed, efficient, and sustainable use of fruit peels across both tropical and temperate regions.